It isn't
But I think-
obvious that, yeah.
Yeah, but I think this is a good. I mean, this is not wrong. I think.
No, that's good. That looks good.
But
That
I think
looks
even
good.
this is the same thing. Like if you look at the way it's structured, when it's contravariant, it's like dx into dx. And it's one form. It's like 1 upon d by d.
Oh, okay. That's-
So you can say that that is what I would say. Like contravariant is vector, and one form is like, or covariant is like a
okay.
gradient operator.
Yeah. Okay, okay. I'm warming up to the idea.
That's what I think. Yeah. And what you were asking, V beta is that thing.
So the order matters.
So I think yeah.
The order
So
matters.
for example, V beta is G alpha beta. You are saying V alpha. But what will be V alpha into G alpha beta?
Oh,
That's valid, right?
that won't work though, because that's a column times a matrix.
Yeah, that's what I'm saying. Like this is like a. So when you write this, you should say like this is like del square, right? When you have two bottom, it will be del into del. This is like any vector v, right? Del square v. It's like Laplace or whatever, but it gives you a function, some function. Eventually, like you will have v0, v1 components of it. But here,
That's not good.
it's like vector and del square, so you will get a matrix. It will be same like this. It will be a vector into all the components. So you will just multiply all those components by all these matrix things by this v alpha. Okay, that's what I think.
All right.
I think
I guess the thing that bothers me about that is it looks like it looks like a column times a matrix, and that seems like that won't work.
column times a matrix. I mean, it will work, right? Why would it work?
No, it won't work.
How does it work? This into this?
It won't work. You'd have to have a row there.
Oh yeah.
A matrix times a column's good, but not a column times a matrix.
So this won't work at all, you are saying, right?
Well, I don't know. I mean, I'm confused now. If I think of it as rows and columns, it doesn't work. If I
Yeah.
think of it strictly as components.
But that's why I haven't. Have you seen this anywhere? I haven't seen this because
I
you
haven't.
always.
Yeah, I haven't seen it.
That's why it's like operator. That's why we haven't seen this. Because
But you know what? I have seen this. I have seen this. You know, I've seen that to raise the index, and by my same argument, that would be a matrix times a row, which you know if the row column thing is true, that should be like that.
right here you said like this you have said.
Yeah, they do.
That is matrix.
They do show using that to raise the index. So I'm a little confused as to whether even I don't remember I've seen that in his book. I'm not sure he always sticks to the row
You should
column.
see where you saw that.
Yeah, I know.
Because I always seen like if they have like upper thing, then they will write p beta here.
Well, okay, that would make sense.
Because
that would make
this
sense.
is always an operator. So
Okay.
that's what I feel like whenever.
Well, yeah, I think you're right.
Yeah.
I think you're right.
So that's why whenever they have something like this, unless first is a row, this worked out fine. You could multiply it,
Yeah.
but otherwise you always do
Yeah.
this.
So that should be first.
Here also this is an operator. That's
Yeah.
why it's first.
I have to go back and look now. Now that I have this idea,
Yeah.
I have to go back and look and see if anybody really says that or not.
Okay, this was good.
You know, I think if you go to any more of these meetups with those guys, I think at this point you know more about general relativity than any of those
Yeah,
guys.
I'm not going.
Yeah,
I was thinking someone will do something like this, but like, especially people who know they can. Like it doesn't take time. We could have just because we just need some push in the right direction.
Yeah, yeah.
But yeah,
Yeah, I
just
got
decided
tired.
to do it.
I got tired of those meetings. But
Uh,
sometimes you can find, some of those, occasionally you find people through that group. What Tina and I did, how we got together at the quantum class. We met people in that group just by going to those meetings, and then we'd meet people. And certain people, like I met you, you know, you find a person occasionally who's serious, wants to do some stuff. And so sometimes just by going you can
Yeah, that is
find
true.
the people. Then you just gotta find somewhere to meet.
Yeah, yeah. Need to find people. That's true.
Yeah.
I think we can find more people. Like once we have, you can also teach me some quantum thing. I haven't looked at it.
Yeah. We have to do soon. We're now, within a few weeks, we'll be gone.
Oh,
We're moving sometime in the next few weeks.
oh, okay.
We're
Okay,
close.
no.
I told you we're moving to Colorado,
Yeah.
right? So we're getting close. In fact, this office, her office goes away on April 1st. That's her last, she gave her notice of April 1st, so.
So if you're free next weekend, we can.
Yeah,
Or
we should,
whenever you're free.
we
I
should
think.
coordinate.
Yeah.
But also, it's gonna get harder and harder to meet in the
Yeah.
office.
No, we can meet anywhere. It's
But, yeah.
we can meet in that thing. I mean, if you just teach me the initial stuff, it will be
Yeah,
easier.
I have a little whiteboard in my apartment
Yeah.
too. We
Yeah, you
could
can
maybe
see
meet there next time.
Okay, so the next, we're making a small detour to see why metric tensor is involved when taking scalar products of two vectors.
Okay.
We first need to note that components of metric are defined in terms of coordinate basis vectors. For example, he has taken Gij here, which is Ei into Ej. It should have been okay. That is what he says.
Yeah, I've worked through that. So yeah, so the if you know the vector, if you know the basis, then you can get the metric from that by taking the dot product of the vectors.
Okay. Yeah. Dot product of the. Yeah, you know that, right? But I think I'll just write it down. Dx square dx.
This is, by the way, this is a case here where it's important to remember that these things are not components.
Yeah.
That's, you know, that really is a dot product between two vectors.
Yeah. So it comes out to this, and this is the Kronecker delta.
Yeah.
So in Euclid, you know that, right? It's but here also I don't know why. Like if you follow his notation, this will be like the operators, right?
Well, see that.
But if new you are here, then they will be like.
Well, it's different for the basis vectors because the lower index basis goes with the upper, goes with the,
Yeah, this thing, right?
you know, so it's more like the lower index basis vectors are more like are the contravariant basis
Contravariants, yeah.
vectors. I mean, I'm a little confused about that too, but you know, the qualities of the lower indexed E should be like the upper index. I think.
Yeah, that's what it looks like. But if you look at it, like metric tensor actually it gives us distance between 2 points, right?
Mm-hmm.
And the distance, like if there's a curve between 2 infinitesimal or whatever, like you get a distance between 2 points in Euclidean, it's like 1 0 1 1 1 and or 0 0.
Yeah.
But for different curves, you can have these components, right?
Yeah. Yeah.
And so metric tensor is like generally it's like Gij, which is like if it's downstairs, it's like a function. Like if it will give you how how the function varies. So because you need this function, right? And how this curve is varying to know the distance between 2 points. Because if it's a straight line, it's like Euclid. But if the curve is weird, you need to know this function, right? How it's varying, so that you can figure out what's the distance between 2 points. And metric tensor basically encapsulates that information, like how the curve is, how the in 3 dimension, how the manifold is. Like if it's 3 dimensional, for example, right? Here it's I goes from 0 to 2, E goes from 0 to 2.
Yeah, so let's put in like this a spherical surface, say, and look at that.
No, I mean it's easier if you put Cartesian, right?
Well, except then it's hard. It's not really varying.
No, but I want to just tell you what it
Okay.
means, or maybe because what metric tensor would give us, like if this goes from 0 to 2, 0 to 2, this will be like 0, 1, 2, 0, 1, 2. Actually, let's not consider Cartesian coordinates. Let's say this is something x, or this is a bad thing maybe. What is a variable?
That's what I'm saying. What if we did a spherical surface? So we have a real thing. It's just.
No, I want to give you like a very general, like everything has something.
Oh,
like
okay. All right.
For example, consider this is like x, but it's not x. I mean, this is like G00, for example.
Yeah, yeah.
Or G01, whatever. Y, W, A, E, H,
Yeah.
G, whatever. So they are not 0. They have some value.
Yeah.
What does this mean? Like G00 means like in the 0th, like the 3 coordinates, for example, not perpendicular anything, and there is some curve or some surface. So G00 is like twice differentiating with respect to the same coordinate. That's different. But G01 will give you how they are related to each other.
Mm-hmm.
So these things are basically they give you how the coordinates are, because this is like one form, right? So it's like a d by dx, like d by d0, d by dx0, x1 something.
Mm-hmm.
So these are giving you how they vary, and then you operate on your vector to get the total distance. So this can be different in different coordinate systems.
Mm-hmm.
But when you operate and on vector, like these are like UV functions, how they vary and all. When you operate on the vector, you get the distance between
Mm-hmm.
2 points.
Mm-hmm.
So something like that. Like if you like at a higher level intuitively, like
Yeah.
this is what's happening. Like you have some surface, it's varying in some fashion, and when you take those like how it's varying into consideration, you get a proper distance because it's not Euclidean. It can be any function, any surface, something like that. Right? The metric tensor will give you that, like how it's basically it will give you how it's varying.
Yeah.
And
yeah,
when you
I see
transform
that.
coordinates, you will get a different metric tensor then.
Yeah.
But if you multiply that metric tensor with your, like this will be like d by dx, d by how it's varying with your x, y. And you get a scalar. That's what they were saying, right? Like when you have a one form and a vector, when you multiply them, you will get a scalar.
Yeah.
That scalar will turn out to be the distance, because this is basically we have the components and you know how it's varying and something like that.
Right.
Can-
Right.
Now tensor transformation, the contravariant and covariant, we already looked at it, it's the same.
Yeah.
think I've already noted this down, so I will rub this. I think we should just write down. I'll try to go and just see for completeness. We have the same. Then one method of constructing a new tensor is by multiplying components of vectors and one forms. So we are saying t, beta, lambda, neta equal to f, beta, w, lambda, a, neta.
Now, here's a question. Do they have to come in the order, in other words, does eta have to come first? Because,
This one?
yeah, I mean, do they have to come in the same order?
I think the way in this book, at least what I saw, they first write this component and then this generally, like if you have a tensor. So this will be like a column, another column and then a row, right? Then they, I think this column can be multiplied by row, right? Column can be multiplied by row, row can be column into row.
Yeah, those two will be okay, and then you get a matrix. It seems like you'd have to put the row, it seems like you'd have to put the row in the middle, actually.
This won't work, right? So this is
Oh, actually, I think you'd have to put the row, yeah, you'd have to put the row first, I think, because, no, you'd have to put, oh, geez.
no, but what I'm asking
Oh,
is,
they,
how do you represent this? Like, it has 4 rows, right? So 4 into 1, right? And then 1 into 4, right?
I think the row has to be in the middle.
No, but this is 4 into 1, right? First is number of rows, and then into column.
Yeah, it's not gonna, here, it needs to be,
This one is 4. Column is 4 into 1.
I think it needs to, if we're gonna go with the row column thing, seems like we need this, because, these two can make a matrix, and then the matrix can, no,
These two
we
can't
wouldn't
make a
get that,
matrix.
we wouldn't get that.
No, but these two can't make a matrix, right?
These two would make a matrix, but then this would make a column.
How will these two make a matrix?
Column times a row is a matrix. I don't think the row column thing works. I don't think it's. I don't-
No, sorry. I mean, this will work then, I'm saying. Because how does this multiply? This is not right. These two should be same, right, for that.
Well, that's okay. That would make a matrix.
No, this is 4 in, no, this is not 4 into 1. What? So
Column
4
times
is.
a row will make a matrix.
Yeah, right. So this will be a 4 into 4, right? This will be this into this into this, this into
Yeah.
Then so this will be a matrix, and then there will be a.
But that's not good. I don't think the column row thing is going to work out when you got
So
three of
your
them
thing
like
would have
this.
worked out, right? If we had this here, it will work out, right? Why won't it work? It will work out. It will be a 4 into 1.
Yeah, but then you don't end up with a. I don't think there's no way you end up with this thing. I think you can only look at this as components. I just don't think the row column thing will work. I don't think. I think you have to. This just has to be
What are the
components.
components?
Just has to be by components. But there might be a question of getting the components in the right order. I mean, the way we have it here, oh, I see, you're putting this on the end because that way we have the operator on the end. So, well, this, I'm very
What is
confused about
column?
this.
Is there a column into column matrix? Does it mean something? Column matrix into column matrix. Does it mean anything?
Well, what it means to me, okay, the only thing I know of that you can do with this is what I call a tensor product, which is not a direct product, but is you know, if this is a 4x4, then you end up with a 16, big long row. But that's that has nothing to do with relativity. That's a the way it's done in quantum information. I don't think that applies to this. Otherwise, I don't think there's any column times column.
So I think we can't look at matrix, but you can say that it's
You just have to look at components.
distance and then operator.
Yeah. So how do you know? So I mean, how do you know this is the order we want?
And this is their order, I don't know. I mean, we don't know
Oh,
what's
okay.
I mean, I'm giving an
You
example.
wrote
This
that.
was that one method of constructing a new tensor.
Yeah.
It's like multiplying vectors and
Yeah.
one parts.
I mean, I was okay with that until I started to realize that there might be a difference in the order. You know, when I was looking at this
Yeah.
before, I thought these could be any order because they're just components. But now that I'm thinking, some of them are
I think
operators.
this can be any order maybe, because
Mm.
this can be like dx into d by dx into dx.
But,
or dx.
but wouldn't these two would give us different?
It will give a different, yeah. So when the order, if you change the order, you will get a different answer. Right?
Yeah. So this now I'm confused. I thought I understood this before, but now I'm confused about how you know what the right order is.
Yeah.
And you know, like, is this a different tensor? You know, is this a different tensor than if I wrote it like this? You know,
I think it's different.
yeah.
I think when you write it like this comes at end. I mean, sorry, if you assume the convention is if you write it like this and this comes first, and here if it comes last, then it's different.
Yeah. So this, I mean, do you get that? Do you understand that? I don't really get what's happening. I don't really understand.
No, I think the way I am thinking is when you have two here, you have square of some velocity or component, whatever vector, and then you are when if it, for example, if it's coming here, you are like operating on that square, like you are differentiating basically. That's what's happening. This is like a function gradient, and you have some other thing, and you differentiate. And here, these components you multiply, and then just this has, for example, neta has 4 things. Then you will just multiply, like you saw in that matrix. This gradient things, you will just multiply by that a into d by dx.
Mm.
That's the difference, I think, because I think this arises because d by dx into something will operate on. It's like an operator, and people are not realizing it maybe, or
Yeah.
they are not implying it, or they are not explicitly saying it, but I think this is what's happening.
Yeah. Well, that's
And we
very
can look at
important.
it more deep.
Yeah, I'd like to look at this more deeply.
But right now that's what we have.
Yeah.
And
I want to go back and look. I'm going to look through some of my other books now to see now that I really recognize the question, if anybody is making this operator function distinction.
and they are saying E beta lambda eta is equal to T prime alpha eta tau equal to F prime alpha prime eta. Basically, they are
Yeah, I
related
get
to
the-
each
I
other
get
by their
that.
differentiations.
I get that.
And then there is a big equation.
Yeah, I remember that. Just the generalization of that.
But I think we should, let's look at it. Yeah, let's just look at it. this is a tensor, this is a tensor. It is like u1 to um 0, 1 to m contravariant, 1 to n covariant. Convert into a different different tensor with 1 to m in
Yeah.
different u and this and beta. This is actually, it just boils down to that basically
Yeah.
calculus
Yeah, I get that.
chain rule, but yeah, we should look at. But even if you see here, when you represent it as tensor, I don't know. I mean, but when you actually, like what we saw, when you actually do that f into w into how the, that's what I was confused. Like if it's f beta w a sorry x and you represent it as d beta a n. Like what will you represent if this is at the end? What will you do?
Yeah.
I mean, I know what's happening actually, but how will you write, what does a tensor look like? I mean, what do you represent that tensor like? Maybe they won't represent it. I don't know what to do. I mean, we'll have to see.
Yeah. I need to go pretty soon. Where are we at in here?
These are rules of tensor algebra. Yeah, we're almost done with the fifth part, and then there is more on curvature. We can do later.
Maybe well, this could. Why don't we stop here and make it mark or something where we are?
Okay.
Because I just realized it was after 6. I didn't need to get.
Yeah, I know where we are. Rules of tensor algebra. Yeah. I will just.
Okay.
Right.
Yeah. This is good. Wow. So this was a very good session. It raised some questions. Neat.
Let me know if you can give me some quantum physics thing. How long will it take, quantum mechanics?
Well, you know, let me, when I get home, I'll try to remember, let me send you the notes from the little class we did. They should be very simple to understand because the class was just based on, the claim was you just needed to know high school algebra.